Hey y'all, in today's video, we're going to talk about another periodic table trend called electron affinity. We're going to talk about how it works and what you're going to need to know, and that's going to be that. Let's go ahead and get started. The first thing to keep in mind whenever you're talking about anything with energy is that forming an attraction is going to cause energy to be released, whereas breaking an attraction causes energy to be absorbed. So in other words, when we learned about ionization energy, it took energy to pull an electron away from a nucleus. All right. So ionization energy, all right, is always you're adding energy to rip an electron away. Electron affinity is a different process altogether. In electron affinity, it's the energy that is released when you put an electron onto an atom. So you're creating an attractive force between an electron and the nucleus. Now, keep in mind, this is going to form an anion, okay? An ion that is a negatively charged ion. So you're adding an electron to an atom that already exists. You're forming an attractive force, so negative energy. This is energy that's being released out as a result of this process. Be careful. It's very easy to make the mistake of thinking that ionization energy and electron affinity are simply opposites. They are not opposites. Taking an electron away is a completely different process than adding an electron in, because in the end, what you're starting with in electron affinity is your atom, your base atom, and then you're adding electrons on top of that. With ionization energy, we're pulling electrons away from your base atom. So you're going in a different direction. Also, the process is simply different because, again, ionization energy is going to take energy to pull away an electron. It takes energy to break attractive forces. Electron affinity is negative energy. It's energy that's being released out as a result of your forming an attractive force. So if we look at this process in what we would see as like a chemical formula, you can see electron affinity, energy is on the right side of the arrow. That's the product side of the arrow. So energy is being released as a result of this process. Ionization energy, the energy is on the reactant side. It is on the side where you're adding energy into this process to force the electron away from the nucleus. Again, they are not opposites of each other. They are completely different processes. Let's look at the periodic table trend of electron affinity. Electron affinity is controlled by Coulomb's law, just like all the other periodic table trends. So it's controlled by the effective nuclear charge and the number of energy levels. As we look at electron affinity, keep in mind that the more attracted an electron is to the nucleus, the greater amount of energy to be released would be when you add in that electron. So an electron added to fluorine, for example, is going to release more energy than an electron added to any of the other nonmetals. Also, we have to keep in mind the fact that noble gases adding an electron is going to bring you up a whole energy level. So noble gases is actually not energetically favorable. It doesn't release very much energy when you add in an electron because the electron you're adding won't be exceptionally well attracted to that nucleus. Remember, this is a noble gas. It already has a full valence shell, and by adding one more electron, you're adding to a new sublevel or not a new sublevel, a new energy level. And as a result, it's going to get further from the nucleus. That's not going to increase the attractive force by much. If we look at a very specific periodic table that shows these electron affinities across the periodic table, you'll notice there are some exceptions to the general trend. Now, the reason for that comes back to the same exceptions we talked about when we were looking at ionization energy and the others. In the end, electron repulsions and electron attractions do vary within sublevels and energy levels as you go from fully filled to half filled and everyone in between. So be aware there is a general trend, but there are also exceptions to the rule predicated on increased or decreased electron repulsions. Now, I'm not going to provide you with any example problems or practice problems in this video because in the end, electron affinity is something you need to know and be able to apply only in definition and practice, not necessarily energetically. I'm not actually going to ask you too many questions this year when it comes to the energy of electron affinity. When we do get to thermochemistry, we might see a little bit of that, but that's not for a few units, so we'll wait till we get there. Today's video was written, directed, produced, and edited by Claire Pang and Ava Ng. Thank you all for watching it. I hope you enjoyed it, and I'll see you in the next one. Please, why am I saying please? Please like and subscribe. Never going to do that. Oh my God. No. God help us. Subscribe button's down below. Anyways, all right.